So yeah. So anyway, chapter 5 is number systems, and so it's not an enormous chapter. It's only 19 slides, thankfully, but it does certainly have some important information in it, especially because I think we've spoken about hexadecimal and binary and a few other things like that in the previous chapters, and so you know, a bit better understanding of those is probably a good thing. So anyway, we're going to look at the binary numbering system and also hexadecimal. So of course, everything a computer does is in binary, and so for us to understand how it works, we need to understand binary. And of course, when it comes to both MAC addresses and IPv6 addresses, it's displayed in hexadecimal, so you should be able to understand that as well. So binary numbering system consists of ones and zeros. Of course, bi means 2, so it's a base 2 numbering system. So of course, decimal, dec means 10, is a base 10 numbering system. And so the reason that computers use binary is it's a lot easier to have some kind of object with 2 states than it is to have one with 10 states, like we have 10 fingers. And so, you know, you can fill something with voltage, or you can have an empty, that's, you know, a 1 and a 0 there. But if you had to have 10 different levels of voltage in a device, it would make it a lot more complex to build and probably a lot slower to read. And so that's why lots of simple ones is actually much better than a few more complex ones. And so that's why we use binary. I'm going to say, if you remember DVDs and CDs and things, of course, there was shiny and not shiny. That's a good and another easy way. Of course, we've already spoken about how data is transmitted, so you can have a voltage for a 1 and a voltage for a 0, or a transition in voltage we were talking about as well. And so 1s and 0s are very easy to do. Of course, hard drives, it's stored in, you know, magnetic poles, north and south. North is a 1, south is a 0, just plucking it there, of course. And so very easy to have 2 states. Now, host servers and network equipment use binary addressing to identify each other. It only translates it in a dotted decimal notation when it needs to be displayed to the human. It doesn't bother with it any other time. Each address is made up of a string of 32 bits divided into 4 sections called octets. And so, of course, yeah, that's of course how the computer deals with it, is a string of 32 bits. And so, of course, each octet has 8 bits, or is equivalent to 1 byte. And of course, we separate it when we're displaying it. For ease of use by people, this dotted notation is converted into dotted decimal. And so, yeah, so that's, of course, how we display an IPv4 address. Now, positional notation is something we use, again, both in binary and decimal. And so what we mean by positional notation is basically that you know, when we're using powers of 10, we have the rightmost column, the units column, is actually that number to the power of 0. Now, any number to the power of 0 equals 1, and so that's why that last right-hand column is always units, because any number to the power of 0 is 1. Then, of course, the next column is that, again, that base number to the power of 1, and of course, any number to the power of 1 is itself. And then from there, the next column, of course, is power of 2, then power of 3. And so, of course, with tens, that makes it easy, because this is hundreds and thousands, and it's all very neat and tidy. And so, of course, if you've got a number 1,234, it means you've got 1,000, 200s, 3 tens, and 4 ones. And so, of course, that's our positional notation, how we understand the values. Now, in binary, it actually works exactly the same, except for one thing. It's got a different base number. And so the right-handmost column is 2 to the power of 0. And so again, that's a value, that's your units column, or your, you know, value of 1. The next column is 2 to the power of 1. So then again, that is itself. So it's 2s, and then it's 2 to the power of 2, 4, and then 8, and then 16. And so with decimal, of course, we just added a 0 on the end because it was tenths. in tens, but of course this is twos, and so we basically double the value for each column as you go. And so of course normally we talk about 8 bits from 0 through to 7. 2 to the power of 7 is 128. And so if you add this, all of these numbers in this bottom row here together, it would actually equal 255. And so that's all of the, if that's all of the values in every column is set to 1, that is what the maximum value is in a byte, is 255. There's 256 possible numbers, of course, but of course the first number is all zeros. So it's 0 through to 255 is all the values that are possible in a byte or an octet. So here we've got an example of a binary number, a little more complex than the one I was talking about. And so there's a 1 in the 128 column, there's a 1 in the 64 column, and there are zeros in all the rest. And so an excellent way to convert binary to decimal is basically you add the values for each column value. And so 128 plus 164 plus no other things. And so that's 128 plus 64, and so that binary number in decimal is 192. And so that's the easiest way to convert binary to decimal, is just to figure out those column values and then add up all the columns that have a 1 in that in their position. And so so here of course we're doing an entire IP address. So there's the 32 bits or 4 bytes or 4 octets, however you want to call it. And so here, of course, we're starting out with a binary number. So it was 192 in the first octet, and it was 168 in the second. So that's 128 plus 32 plus 8. And then the next octet was 11. So it's 8 plus 2 plus 1. And then the last octet, we've got 8 plus 2, which of course equals 10. And so that's this long string of binary numbers here ends up being 192.168.11.10. Now, how do we convert decimal into binary? We've pretty much spoken about binary to decimal. That's pretty simple. The process for going in the opposite direction, if you know the decimal number, you want to convert to binary, well, you basically have to go through a bit of a process. It's not a complex process, but it's a process nonetheless. So of course, to start with, because we're talking about 8 bits, it has to be a number less than or equal to 255. And then from there, basically you go through and ask yourself some questions. And so the number you've been given, is it greater than or equal to 128 basically? And if it is, we need a 1 in that column. If it isn't, we put a 0. And so then if we do use a 1, we then need to subtract 128 from that number to see what is left that we need to assign to other columns. And so from there, you then ask, is the remainder greater than or equal to 64? If it is, again, we put a 1 in a column, and then we subtract the 64 from that remaining number we had before, and then we've got what's left, and so on. So we keep asking the question for 32, 16, 8, 4, 2, and 1, and that's basically how we go through the process. We will go through it as an example in the next slide. So here we've got the number 168, and so we go through the question, is 168 greater than or equal to 128? So yes, it is. And so we put a 1 in that column, and so we subtract 128 from 168. And so, of course, the value left is 40. So the next column, is 40 greater than or equal to 64? No, it is not. And so we put a 0 in that column. All right, the next question, is 40 greater than or equal to 32? Yes, it is. And so we use that, we put a 1 in that column, and then we subtract 32 from 40. We have 8 left. So, of course, 8 is smaller than 16, so that's a 0. It's exactly 8, so that's nice. And so we've got 0 left when you subtract 8 from 8. And so then the rest of the columns will just all be 0 because, hey, we've already got 168. And so that's the process of getting from decimal to binary. Again, it's not difficult. It's just, you know, You just need to know the process and maybe work through it a few times to figure it out for yourself. Okay, so when routers and computers only understand binary while humans work in decimal, it is important for you to gain a thorough understanding of these two numbering systems and how they are used in networking. So of course, yeah, certainly is useful, especially when you start what we do in some later chapters. When we start doing subnetting, you actually do need to break numbers down into binary so you can then split the networks up. Okay, so the hexadecimal numbering system. So of course, hexadecimal is how we display IPv6 addresses, but it's also used for MAC addresses as well. So to understand IPv6 addresses, you must be able to convert hexadecimal to decimal and decimal to hexadecimal. So hexadecimal, of course, is a base 16 numbering system. So we have 0 through to 9 plus A through to F, which of course is what this one here is showing. So there's 16 possible values, 0 through to 15, basically, as this column here is showing us. And so basically the easiest way to do a conversion is to basically do these three columns side by side. So you can count from 0 through to 15. You might want to do hexadecimal next. That's probably what I'd do next. But anyway, and then you need to convert those numbers into binary. And so this is the typical way that most people do the process. And so basically we're going to go through an example. And so IPv6 addresses are 128 bits in length. Every 4 bits is represented by a single hexadecimal character. That makes an IPv6 address a total of 32 hexadecimal characters. The figure shows the preferred method for writing out an IPv6 address, with X representing 4 hexadecimal values. For each 4 hexadecimal character group is referred to as a hextet, because of course there's 4 bits per character and there's 4 characters per sort of separation here, and so of course 4 times 4, there's 16 bits. That's why they call it a hextet. Now, how do we convert decimal to hexadecimal? So what we often do is convert those decimal numbers into 8-bit binary strings. Then we divide the binary strings into groups of 4, starting from the rightmost position, convert each 4 binary numbers into the equivalent hexadecimal digit. Now, basically, you can go directly from decimal to hexadecimal and vice versa, and that will work, but it's sort of a complex way to do it. And so using binary as an intermediary is sort of simpler to get your head around. And so again, we're doing the example of 168. So if you remember, it was 128 plus 32 plus 8. And so we've basically got 2 groups of 4 bits. And so it's 1010 is the first 4 bits. And then there's 1000 as the second group of 4 bits. And then we basically refer back to that table again. And so we can see that this is actually 8 plus 2, so that's 10. And so 10 in hexadecimal is A, of course, because it's 9A, isn't it? So 910. And so that's why that value was A. And the next one is 8 plus 0, and so it's an 8. And so 168 converted into hexadecimal is A8. And so, as I said, basically using these tables that we converted before, we had 10 or A, and so 1010, and so you go just look straight across, there's your A, and the 1 and 000, of course, is 8. And so that's how you get your A8, is from bit patterns, basically. Now, hexadecimal to decimal conversions. Again, we normally go from hexadecimal to binary and then binary to decimal. And so basically the steps are: convert the hexadecimal number into 4-bit binary strings, convert the 8-bit binary groupings and starting from the rightmost position, and then you convert each of those 8-bit groupings into a decimal digit. So we've got a number D2. Now D So A is 10, B is 11, C is 12, D is 13. So basically, we've got 13 and 2. So we've got to convert, so basically 13 in binary is 8 plus 4 plus 1. So, of course, 12 plus 1 is 13. And then here the last number was 2, and so it's just 0, 0, 1, 0. So you then jam those two bit patterns together, convert that into decimal. And so, again, you need to add 128 plus 64 plus 16, sorry. Yeah, 16, sorry. Then 2, you add them together, and it ends up being 210. So that's the process that we normally go through. So that's the end of the chapter, not a big chapter. And so, of course, binary is a base 2 numbering system that consists of numbers 0 and 1. We call them bits, which of course is short for binary digits. Decimal is a base 10 numbering system that consists of the numbers 0 through to 9. Binary is what host servers and networking equipment uses to identify each other. Hexadecimal is a base 16 numbering system that consists of numbers 0 through to 9 and A through to F. Hexadecimal is used to represent IPv6 addresses and MAC addresses. IPv6 addresses are 128 bits long, and every 4 bits is represented by a hexadecimal character for a total of 32 hexadecimal digits. To convert hexadecimal to decimal, you first convert the hexadecimal number into binary, and then convert the binary number into decimal. And so to convert decimal to hexadecimal, you must first convert that number to binary, and then you just look up the bit patterns and put it into hexadecimal. That's the easiest way to do it. So there is the logo, and so that's the end of the chapter. It's not a big chapter.